So today we're going to talk about another way to measure an angle on a circle. And we call that measure a radian. So a radian occurs when you take the length of the radius and you lay it along the circumference of the circle. It doesn't go all the way around, it stops right about there. So when the length of the arc is the same as the length of the radius, then the measure of the angle formed is 1 radian. That's our idea behind radian measure. So we're kind of relating the angle measure to the length of the arc. That's really what's going on here. So a few questions about that. First of all, how many degrees are there in a circle? Well, we know for many years that was 360 degrees, and it hasn't changed. We also know that the circumference of a circle is equal to 2 pi times whatever the length of the radius is. So now, how many radians would there be in a full circle? Well, remember, whatever the radius is, that's the radian in terms of the arc length in the measure. So really, there's a total of 2 pi radians in a full circle. So a full circle has 2 pi radians. So then in a semicircle, which is half of a circle, there are pi radians. And this last answer is really the benchmark that we want to follow, because what we want to start with today is converting between degrees and radians. So it's a simple multiplication. If we want to convert degrees to radians, we're going to multiply by pi over 180. You're going to find that what that does is it introduces a pi into your answer. Then we're going to convert radians to degrees. In order to do that, typically we have to remove the pi. So we'll multiply by the reciprocal, 180 over pi. If you're in your textbook and you take a look at example 1, there's a few examples here. I want you to take a look and see if you can figure what those out. I'll wait, don't worry, pause the video. Okay, let's convert 20 degrees to radians. So I'm going to take 20 degrees and I'm going to multiply it by pi over 180. Now you can be really lazy and write it as 20 pi over 180. But I want you to notice a couple things. Do you notice that you can reduce 20 over 180? And that 20 goes into 180 9 times, and 20 goes into 20 once. So actually we can say that our answer is pi over 9 radians. Similarly, let's convert using 56.5 degrees. And this one's a little bit uglier. And the reason why is because I don't think 56.5 and 180 cancel. And yeah, you can write it as 56.5 pi over 180. But this is a case where maybe we want to express it without pi, just as a decimal. So if you go to your calculator and do 56.5 times pi divided by 180, you should get it to be about 0.986 radians. I'm going to go to 3 significant figures. That's pretty typical. So we'll go to 3 sig figs, 0.986 radians. Hey, let's go the other way now. If we're going to go from 4 pi over 3 radians to degrees, let's multiply 4 pi over 3 times 180 over pi. What you might notice is that the pi's cancel out. You'll also notice that 3 goes into 180 60 times. So 4 times 60 is 240 degrees. So 240 degrees is 4 pi over 3 radians. So that's how we convert back and forth from radians and degrees. Now, if we go back to geometry a little bit, what you might remember is that this shaded region is called the sector of a circle. So you have a radius of the sector, you have some angle, let's call that angle theta. And in geometry, if we're going to talk about the area of a sector first, you might remember that the area was actually a fractional part of the whole circle. So theta over 360, I'll make a better looking theta. That theta was terrible. Theta over 360 times the area of the circle. So it's a fractional part of the whole area. But remember that this is in degree form. And in a circle, there are 2 pi radians. So what I'm going to do is I'm going to change my 360 degrees to the number of radians. And watch what happens. This is really pretty stuff. You can probably cancel a few things out. You might notice that the pi's cancel out. And what I'm left with is for my area of a sector is that the area is equal to 1/2, because I'm dividing by 2, times the radius squared times theta. 1/2 r squared theta. So if you multiply the angle in radians by the square of the radius, divided by 2, oh, beautiful things. The arc length, remember, is a percentage or a fractional part of the circumference. So we knew that arc length from our geometry lessons was theta over 360 times the circumference, which is 2 pi r. But doing a similar thing, let's change the 360 degrees to 2 pi radians. Oh, you want to talk about beautiful stuff, right? Look at this. 2 pi, bye-bye. So our length of the sector then, or the length of the arc, is just the radius times the angle in radians. Those are some beautiful things. Wow, radians are so pretty. I like it. Cool, let's practice a couple of these. This is from section, or page 512, it's example number 2. You're asked to find the area of the sector and the arc length. The area of the sector would be this, or the sector and its arc would be defined by that part of the picture. Take a moment, see what you can do. Okay, let's find the area of the sector. We know that the area of the sector was 1/2 r squared theta. And hey, here's a good thing in your ID course. Write down a formula, write down your substitutions. Our area is 8. Our radian measure is 3 pi over 4. And let's multiply all this out. And I see a lot of things that are going to simplify here, so I'm going to leave it in terms of pi. So 8 squared is 64. So I get 1/2 times 64 times 3 divided by 4, all times pi. So let's see what we can do. How about we do this? 4 goes into 64 16 times. 2 goes into 16 8 times. So my area turns out to be 24 pi. Cool. Let's throw units on there. And if we're looking for the length of the arc, remember, it's the radius times the radian measure. So we're going to multiply 8 times 3 pi over 4. And when we cancel some things out, I believe we get a total of 6 pi centimeters. Pretty nice stuff. I like it. One more example that we can do. If you take a look at example 3 on page 512, now we're looking for the area of the shaded region. See what you can do. All right, so what I'm recognizing is the area of my shaded region is going to be the area of this sector minus the area of this triangle. So I got to do the sector area minus the triangle area. So let's see, the area of our sector is going to be 1/2 times the square of the radius times the angle. And then we have to do our area of a triangle formula. Remember that great one. It was 1/2 times the lengths of the sides times the sine of the angle. Oh no, sine of 2 pi over 3. Ugh. So maybe we'll do this. Let's convert 2 pi over 3 to degrees. We'll do it down here. So 2 pi over 3, I got to multiply it by 180 over pi. My pi's cancel. 3 goes into 180 60 times. 60 times 2 is 120 degrees. Does that make you feel a little bit better? So let's see, 6 squared is 36, half of that is 18. I'll just simplify in parts for right now. And then I'm going to get 1/2 times 36, which is 18. Let's just write down 18. Times the sine of 120. And do you remember that the sine of 120 is radical 3 over 2? Oh, it'd be great if you remember that. So now if we simplify a couple things, let's see. 3 goes into 18 6 times 2 is 12. So we get 12 pi over there. Yeah, 12 pi, right? 18, 3, 6 times 2 is 12 pi, yep. 12 pi minus 18 times, and the sine of 120 is radical 3 over 2. So if you want an exact answer, it's 12 pi minus 9 radical 3. That would be a nice answer to get. Very good. If you want to go to your calculator and get 3 significant figures, you can do that as well. Nice job, friends. Nice job.